Rommulo Conceicao, can you hear me? That's okay? No, wait a minute. I have my, wait. And now? No, I don't think that's working. Probably it's here. I don't know. Can you hear me? I don't know what's happening. É, não tá. Jesus, eu devo estar com a voz bem baixa. And now, can you hear me? No, it's not working. Let's see.
Yes.
And now, can you hear me? Yes?
Yes.
That's good. So I'll take this in my hand. So first of all, thanks for the organization to invite me for this talk. It's a brilliant opportunity to show you our work, and a very nice opportunity to be together discussing this kind of subjects. And so I came from this University of Rio Grande do Sul, it's the south of Brazil, and have this high pressure and low pressure experiments laboratory over there. And I'm going to show you two different topics. I had this kind of title. I have to go like that. So we are thinking about, for a long time, we've been thinking about the roles of the volatiles, CO2, water, nitrogen in the mantle. So we are going to see what's happened with these volatiles in the Lithosphere-Asthenosphere Boundary. And then you're going to see the storage of them. It's going to be related to the last talk of Caetano, and probably you're going to do some ping pong during the talk, probably. So it's a work with lots of people that contributed, lots of laboratories that help us to do this kind of work. So I'm very happy, and thanks for everybody. Guys. I will do this. Yeah. No. Yeah. So the topic that we are going through is the introduction, high pressure experiments, and some discussions for the first topic. And then you jump to lower pressure, drop down the pressure, and go to the introduction, low pressure experiments, and some discussion, then finally the acknowledgements. You have the two volatiles that we have been working currently are in this system, that COH, and depending on the oxygen fugacity that we are considering, they can be CO2 plus water when you are in the high oxygen fugacity, but when you drop the oxygen fugacity, and you can go to carbon itself, hydrogen, molecular hydrogen, or any kind of hydrocarbons. So we are trying to understand the behavior of these kind of elements and the speciation in the mantle. What's the effect of all of this? And I was talking to Bill during the coffee break about the estimation of the CO2 and water in the mantle. And I was very surprised because it's still a question that we have to address for the research. We don't know about the real amount of volatiles, but I think that it makes lots of effects. We've been talking to Victor Sasek about some models, and we're going through this as well. But there are some estimation, and I brought here some estimation of amounts of CO2 in the mantle, but also the time that's spent to pass one CO2 from one environment to another one, from one reservoir to another one. But still, we need to work on this. We need to work on the quantification of the volatiles in the mantle. Thank you. Also, but you have these kind of things. You can think about the CO2 and carbon that came from the beginning of the Earth, but you understand that it can be recycled via subduction. So subduction brings the CO2 in the surface of the Earth that can be in different kind of speciation, but probably the most important is the CO2, and bring back to the mantle. And once it happens, it changes the oxygen fugacity. It can keep the CO2 in there, but depending on the oxygen fugacity, it can bring to methane or any kind of hydrocarbons. But the point is that every time that the CO2 reach one part, it reacts with the rocks and promote lots of reactions in different kind of mineralogy and things. The same happens with water. So you can bring water, okay, water can be in the earth from the beginning, the mantle spread, etc. But we have also this mechanism of the subduction that can bring water from the surface to the mantle. And it can have different kind of materials, different kind of minerals that can do this kind of roles. So we have the hydro minerals, sort of amphiboles, phlogopite, clay minerals. I love clay minerals. I think that we don't work enough with the clay minerals in terms of high pressure and in terms of the, how to say, the role of this in the subduction to bring the volatiles, all of the volatiles into the mantle. I will show some works that I've been working with. But also, I put here there the celadonite, lauranites that are some kind of clay minerals that I've been working with. But you have the serpentines, some phase A, phase E, 10 angstrom phase, that's this kind of mineral that happens in the experiment, but you didn't find in the nature. Probably you're going to find some one day, but they promote lots of they can carry lots of water, and if they exist in nature, so they bring these huge amounts of water into the mantle. But also we have these these normally anhydrous minerals, olivine, pyroxene, garnets, and etc. that can bring the water to the mantle, depending on the pressure, depending on the temperature. As more pressure you have, more water you have in this kind of minerals as well. So you have then you reach the transitional zone and the lower mantle and have this kind of ringoidites, things that can bring stishovite and post-stishovite that carry lots of water as well, please. I think that's jumped one slide. I'm not sure. Okay, so yeah, can you pass? Yes, that's okay. Here I bring you some results of some experiments that we've been working with the smectite, for example. So in these diagrams, we got this smectite, and we put it in the interlayer. Smectite is a 2,1,2 clay minerals that can expand, and it has an interlayer that we can put lots of cations. So we've been working with this kind of mineral, putting in high pressure, and we have these three kinds of smectite: the potassium smectite, NH4 with the nitrogen smectite. We replace the calcium. We substitute the calcium by potassium by NH4, and calcium by trace elements. We use the lanthanum to see what happened with the smectite. And you see that when you work with this kind of minerals with high pressure and high temperature, it changes the mineralogy, but changed to another mineral that also can keep water inside of the structure. So in this diagram, I cannot point this, but in this diagram, you can see that smectite stays stable for a long time, but it becomes kind of a muscovite or IS that is like iolite smectite is a kind of a very complex kind of clay minerals, and it gets stable, and it can reach pressure around 7. We've been working up to 7 GPa. And you see this transformation of smectite into up to mica kind of minerals that grabs this water plus this kind of elements as well. Can you pass another one? So if you those lines that are there, the red one is the hot subduction style, and the ones that's in blue is the cold subduction style. So when you see the blue line that represents a cold subduction style, it means that the subduction is the slab go deeper in order to reach higher pressure instead of reaching higher temperature. So if you get this kind of a style in the subduction, you can see that you can bring all of these minerals into the mantle, because the temperature doesn't increase a lot in order to break the minerals and release the volatiles. So if you have this cold subduction style, you can bring all of these volatiles, nitrogen as well, into the mantle, at least up to around 6 GPa, 7 GPa. And here, we've been also working with another kind of minerals, a clay mineral that's quite nice, that's the selidonite. You got the selidonite in altered basalts. You got the basalt from the ocean floor that has some selidonite plus pyrite, and you put these assemblies in high pressure, up to 7.7 GPAs as well. And for us, it was surprising for us that selidonite is very stable. It lives together with coesite, for example. And we in this kind of diagram, you observed that pyrite becomes pyrrhotite. So you have the selidonite that gets stable. In the end, it changed to garnet, but it brings water in until it destabilizes. And you see this kind of difference in terms of oxygen fugacity because pyrite becomes pyrrhotite, so it changes. It promotes some kind of redox reaction once this kind of transformation happens. Okay, all of these are published in applied clay science journals. That's very nice. I suggest you to read a little bit about this publication. And and as I was saying, currently I'm very interested in what happened with stishovite and post-stishovite. We have the equipment that can reach 25 GPA, but so you are in the range of the stishovite. We are thinking about putting some water. There are lots of works on this, putting some water in the stishovite and understand what's happening. So here I brought this diagram that showed us that lots of hydrogen, lots of water can go inside. And when stishovite became post-stishovite, it can grab more water still. But also you have the decompression of all of these minerals that can release the volatile. So it's very important to understand the going down, that the pressure increase to put this kind of volatiles. But it's also important to understand the decompression of these minerals once you have the uplift of the mantle, the rate of the uplift, and see what happens when it's released or if it doesn't release as fast as this uplift happens. Anyway, so more of this, so you can bring all of these volatiles inside of the mantle. Okay, you can be there forever, but you have in the Earth, probably the only planet, I don't know, that has this kind of system that can bring back the volatile from the surface to the interior of the Earth. And I keep thinking that's a very interesting mechanism to keep life alive, because it's very interesting to keep the volatiles, the amount of volatile in the planet in order to have life alive. Anyway, if you think, for example, in terms of the closing of the Gondwana, Vitor was talking about the Amazon, etc. So we are very, we keep thinking about this closing of the Gondwana. The closing of the Gondwana, it depends on loss of the subduction that happens before. So all of this closing that happened with this craton, etc., consumed lots of slabs. And you have lots of data, isotopic data, and etc., that show us that all of this subduction that happened before metasomatized the mantle in alkalis and volatiles, and then the response of this metasomatism was the magmatism that happens everywhere. So here, for example, I have some magmatism that happened onshore. For example, some alkaline lamproites that happens in Paraguay 255 million years. And when you go to what Caetano just showed us about the Paraná basalts, for example, you see this kind of some kind of evidence that we have this basalt that is related to this metasomatic mantle. So probably the expression of the metasomatic mantle, at least locally, is very important. You have to consider this in the models. During the day, you've been listening lots of geodynamic modeling, calculation, etc., thinking about this kind of a dry mantle. Okay, in terms of global, I think that you can consider this, but locally, maybe it's a provocation, guys. I think that probably you need to put a little bit of water in the mantle to see how the thing goes. At least in this reality, in our reality here, when we think about the Paraná basalt and blah, 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 you have this evidence that the mantle was very metasomatized. And the expression of this metasomatism you have everywhere. You have the onshore magmatism. Okay. Can you pass, please? And you have also offshore the magmatism. Okay, you have this parallel of the Paraná basalts in the basins of the coast in Brazil that have the same kind of signature that suggests us that you have this kind of metasomatism, and so you have to understand that the mantle was metasomatized, and it was, if it was metasomatized, it was metasomatized with elements, alkali elements, but plus volatiles. So, okay, if you have the opening of the Atlantic opening, I mean the breakdown of the Gondwana, once you have the uplift of this mantle, it's gonna express the composition of this. So every time that you have, here I have this kind of, I'm sorry, I cannot show you the pointer, but the idea, okay, in the first diagrams in the right side, you have this uplift that's happening in the asthenospheres coming up, and what's the motivation of this talk? Thank you so much. So the motivation here is, okay, once you have the middle, here. Once you have the uplift of the asthenosphere, and if this asthenosphere or the lithosphere is metasomatized, what happens with the volatiles during the opening of the Atlantic? What happens? So what happens if the volatile goes up and find the air? It has to pass through the lithosphere, or what happens if this volatile reach a bunch of water, sort of a reservoir of water? What's going to happen? And so here we have this kind of evolution of the uplift of the asthenospheric mantle during the opening of the Atlantic. And here in this cartoon is a very sort of dizzy cartoon. I'm trying to show that we have previously, we have the subduction, we have the eclogitization of the slab, then we have this kind of cemetery of old slab that probably all of these are eclogated. And then you can or you cannot have this kind of effect of plumes. The plume could bring some kind of elements or could bring just the thermal gradient, whatever. But once this mantle is metasomatized with this eclogite slab that was from the closing of the Gondwana, what happens if this starts breaking, this lithosphere starts breaking, and finally the uplift of the mantle release all of this volatile and blah, blah, blah. What's going to happen? So the goal is, we are in the first part. So the first part, the goal of the first part is understand the behavior of the sea, of carbon, oxygen, and hydrogen in the system under high pressure in the context, of the Lithosphere-Asthenosphere Boundary in different kind of pressure. We work with 2.5 GPa, 4.5 GPa, and 10 GPa. Tomorrow and after tomorrow, we have the possibility to talk to the person that was working with this, that's Carol Polotic. She's gonna have this poster on there. It's her PhD, so we have more time to discuss in the poster, please. So the idea is very simple. We performed some experiments, a kind of sandwich experiments. So where we put in the bottom layer and have the upper layer. And we make this very interesting experiment. So we have this lithosphere layer that is here. And we thought, okay, if you have this subduction, you have this metasomatism, probably the lithosphere was also metasomatized. And it was metasomatized with the elements that release faster than the other one, so potassium. So we thought about this lithosphere, that's the upper layer of this capsule, as this kind of a mantle. That's this NHD mantle is a mantle that was depleted before, and then it was metasomatized. So it's a depleted mantle, metasomatized with potassium and water. So you put a little bit of potassium, 0.70% of potassium, and 0.8% of water. And in the bottom of the capsule, we will put a layer that's composed of two kind of composition. One is the perlite composition. Everybody was talking about this during the day. So it's the perlite composition that's a fertile mantle. But you put also 70% is the perlite and 30% is the eclogite plus CO2. So the CO2 is in the bottom layer and the water is in the upper layer. Oh, I'm sorry, no worries. So all of this was put in the pressure, 2.5, 4, and 7.7 GPa, and 10 GPa, and I'm going to see the results. But first, so here's the composition of the starting material. Here's the NH mantle composition, the depleted mantle composition plus potassium. Here's the perlite composition, and here's the eclogite composition plus CO2. Okay? Please. That's our machine. We've been working with this machine. It's a toroidal machine. It's a belt machine, sort of. It's very easy to work with. It's a Ukrainian-Russian machine that's quite nice to work with. So we have these chambers. These two chambers, the sample goes inside. This is the profile that's toroidal profile, please. And in this toroidal profile, we put this gasket. Inside of the gasket, we have all of this assembly to transmit the pressure inside of the capsule. That's this tiny capsule. So I have the graphite, that's the furnace. I have the parafilites to keep the temperature inside. I have the boron nitride that transmit quite hydrostatically the pressure to the sample. Because in our experiment, we want to keep the volatiles inside, so we put this sleeve and caps of parafilites in order to keep the water, the volatile inside, and finally the capsules, that's platinum capsule or palladium or even gold capsule, depending on what the volatile that we want to trap inside. Okay. In order to go to 10 GPa, we've been working with this multi-envelope from in Germany with colleagues in Münster, in the Mineralogy Institute in Münster. So it's a different one. So here we have the octahedral and all of this assembled in order to reach the pressure. We've been working up to 10 GPa. That's okay. And here you can see the results of the experiments itself. So here we are showing you the 2.5 GPa, sort of around 75 kilometers. Here in the subsolid condition, for example, you still see the two layers of the capsule. So you see the lithospheric composition and the asthenospheric composition. We see the mineralogy. That's quite interesting because in 2.5 GPa, you can stabilize amphiboles as the hydrous phases in the lower layer, in the lithosphere and the asthenosphere. But once it starts melting, we preserve the amphibole. And once here is in 1100 Celsius degree, and then in 1200 Celsius degree. In 1100 degree, you still see the interlayer in the lithosphere and the asthenosphere, but in 1200 degree, you don't see anymore. You see a kind of a very sort of homogeneous place, but you see that the minerals that's basically CPX plus olivine, they sink in the bottom of the capsule and have lots of glass. That's the melting composition. So here we have this kind of a 22% of melting and all of these minerals that's stable, but they concentrate in the bottle, but they are spread as well in the capsule. Okay, if you go a little bit further to 4.5 GPa, we still see the interface in between the lithosphere and the asthenosphere in subsolid condition, and 1100 Celsius degree as well, and 1200 don't see anymore. You see almost the same kind of behavior, but it's funny because you have this kind of composition here. You have some minerals that goes up and some minerals that goes down. For our surprise, in 4.5 GPa, we still have amphibole stable. I was expecting that amphibole was finishing or destabilizing around 3 GPa, but in this composition, stabilize amphibole at 4.5 GPa. That's quite interesting, this. Also, in these two conditions, you saw that the diopside, for example, it grabs some water inside. So in these two compositions, 2.5 and 4.5 GPa, CPX gets some water inside of its composition, so it can be a reservoir of water, plus this mineral plus the hydro minerals as well. Okay. I don't want to push that hard, but this is a image of subsolids conditions. So you can see here the limit in between the lithosphere and the asthenosphere. That's the subsolid conditions at 9 degree and at 900 Celsius degree at 4.5 GPa. And could you pass? And this, can you go back and forward? I don't know if you can see, but you can see this kind of a porosity that happens here. And if you limit this porosity, it seems, I'm not sure about this, but I want to be sure, that's the percolation of the CO2 in the capsules that try to find a track. And you have this reaction that is happening because when CO2 starts percolating, it transforms lots of mineralogy in CPX, or garnet with calcium. So we have this kind of, when you go through this kind of a porosity plus the minerals, you can see this kind of tracks. I keep believing, I cannot say and attest really, but I keep thinking that probably it's the percolation of the CO2 because you don't see the mineralogy of CO2. You don't have the reservoir in mineralogy that grabs CO2, but you can see that the water was there, but CO2 wasn't. So because of this kind of texture, I keep thinking that probably the CO2 goes like that. Okay, so if I'm right, I'm not sure if I'm right, but if I am right, all the time that you have this kind of uplift, you have the melting, you have the stable or subsolids condition or in the melting after the solids condition, but the CO2 is always releasing from the mantle, and always releasing from the mantle and trying to react and going upwards. So maybe it's the gassing of the mantle itself. It is the gassing of the mantle itself. But water has some reservoir. The water has some minerals that can grab the water, the hydrous minerals. Even dioxide can get some water, so water is stable on those conditions. Yes? However, when you go deeper to 10 GPa, for example, then you finally have magnesite. Magnesite is very stable, and here you have this, in subsolids condition, you have magnesite that's stable together with the mantle mineralogy, and when you go a little bit further in terms of temperature, from 1000 to 1300, you still see the Lithosphere-Asthenosphere Boundary. And once you increase a little bit, you see lots of melt. 50% of melt is a huge amount of melt. 60% of melt, huge amount of melt in 1500 degree. But the carbon, it stay either in the minerals as magnesite or in the melt itself. So this, we've been analyzing this melt, it has lots of amount of the carbon, CO2. So in this kind of pressure, you are in higher pressure, 10 GPa, and so in between 4.5 GPa and 10 GPa, you see the reverse. Before, in pressure lower than 4.5 GPa, CO2 goes up, water stay. In here, you have the opposite. CO2 stay, water goes up. Probably when water goes up, it hydrates the mineralogy that is upwards and stabilize the hydrous minerals. That's the one of the ideas. When you look to the composition of these melts, for example, you see the complete difference in between the 10 GPa and 2.5 and 4.5 GPa, especially in the silica contents. So here you have this huge amount of silica independent of the temperature, but when you go to 10 GPa, it drops a lot. So more questions about this, Carol is there tomorrow for the poster, and it could be very nice to talk to her. Okay? Yes. So more. Yes, just emphasizing the elements that I just talked about. More elements. So you see all of the alkalis as well. So about the discussion about here, so you have this kind of when you're in this kind of pressure, water stay in minerals or in kind of non-hydrogen minerals. But once you go to 10 GPa, the opposite happens. So that's the conclusion of this first part of the talk. You have more. So, if the So if the CO2 isn't there, and if this is not that much, the oxygen for gas is not that high, if the oxygen for gas is low, what could happen with this assemblage? So we've been performing also in the same kind of pressure, 2.5, 4.5, and 5.5 GPa. You got the magnesite put together with brucite and water, so we're trying to have the CO2 plus water system, and put inside of the capsule and try to reach the oxygen for gas in between the CCO and IW. CCO, carbon, monoxide carbon, and iron vostite, oxygen for gas. So we've been performing some kind of experiments in this kind of condition with this assemblage of minerals and water. And you've been trying to analyze the volatiles. In order to analyze the volatiles, have to make the device. You put the capsule here, you crash the device inside of the, you crash the capsule inside of this device that was previously vacuum cleaned. And then you carry a gas to put in the chromatographer and analyze the gas that was releasing from this composition under the pressure. Okay, here you have the mineralogy. So in low pressure, for example, we have this magnesite stable brucite and iron, a little bit of iron that was put inside. Vostite was breaking. So we have all of this mineralogy. I want to call attention about the stability of the this magnesium ferrite, but also some kind of carbonates that has magnesium or iron and with water. So water, again, is stable in this kind of condition. But once you go to higher pressure, you stabilize vostite and periclase. But I want to show you the results of the gas. From 2.5 to 5.5, you see the formation of methane, ethane, and butane. And okay, here you have the standards to analyze these three hydrocarbons. But once you work a little bit in chromatography and see this time of the chromatographer, you see you don't have the patterns to analyze all of this peak here, but this peak is in the region of more complex hydrocarbons. We are still working with this data, but for sure you have this data is okay. So I want to show you this graph here that shows us all of the results in terms of the gas in these different conditions, 5.5, 2.5, etc., 4.5 and 2.5, where you can see that the pressure seems that increase the complexity of the hydrocarbons. It changes, for example, here is this green line. You can see that the pressure, once the pressure acts, you can increase the proportion of butane against methane. But if the temperature acts, it breaks the molecule. So it seems that the pressure increases the chain, but the temperature make this simple. So I will go fast because I don't know how long I have. 50 minutes, I have plenty of time. I think so. So we are dropping the pressure down. Caetano already told us about the CO2, so I go fastly about this. But so we have to think about what to do with the CO2. We have to store CO2. We have to do lots of mechanisms, and lots of laboratory needs to go on this. We are going on this as well. And as Caetano was talking to us, we have this plenty of material to work with. Taking as an example, Valula and Carbfix as an example, one in Colombia, the other one in Iceland. Both of them are succeeding. But it's funny because in Iceland, for example, the geothermal is very high, and they have olivine that's beautiful to react. Olivine react a lot. And when you go to the Paraná basalt, for example, you don't have the olivine. If you have once, it's changed for another kind of mineral, clay minerals. That's very important as well. And unluckily, you don't have olivine, so you have to understand about the reactivity of these basalts. And also you don't have the thermal gradient that you have there. So our thermal gradient is very low. You have probably 45 degrees per kilometers. So it's completely different from that. And also, another thing that we have to concern about is the hydrogen production. We need to understand, I'm a geologist, so we need to understand how to find hydrogen. If you need to make the transition, I don't know if I'm Brazilian, I'm geologist, I think that we still have to use hydrocarbons, oil, and etc. Okay, you have this, you have to use this, but you have to make the change. And in order to make the change, you have to have the ideas. You have to work with new ideas. How to prospect it, where I can find it. And currently, we've been trying to find these ferrite circles. That's a geomorphological expression, but it's not enough to find the hydrogen itself. What's the mechanism to release hydrogen from the mantle? What's the mechanism to produce hydrogen via serpentinization, whatever? You need to find this. And you have this you have this well-known production of hydrogen in Mali. It seems like a sustainable production of hydrogen that happens, and so it's a case. Everybody's trying to study this case, although there is not much information published, but it's very interesting. So two things that our group are concerned about is the storage of CO2 in production of hydrogen. Yes. So that's the goal, trying to understand the production of hydrogen and sequestration, capture of CO2, promoting some low pressure experiments as well. Anyway, so I will not go through this because I don't have very much time, and Caetano we're talking about this as well. So we have the Paraná basalts that spread everywhere, locally at least. So we have this huge amount of basalt that's very interesting. We have this, when you look in this diagram, you have the high titanium basalts and the low titanium basalts. In the south, they are more frequently the low titanium expression. In the north, they are high titanium basalts. Here's the profile that shows us the depth of the basin. So you have the deeper epicenter in the north, and it's a little bit shallower in the south. We've been working in samples from the south, so low, and in fact we've been sampling the high titanium and low titanium basalts and try to understand how they react. The titanium doesn't make any change. What makes the change is the mineralogy itself. And here I'm showing you the gradient, the thermal gradient that's very low. So okay, you have to deal with this. You have low thermal gradients, and you have to promote the reaction with these basalts. So how to do this? Anyway, the expression of the basalt that interested us a lot. So you have the massive basalts, that's in this picture here. You have the basalt with the vesicles. So if you think straightforward, okay, I want to capture CO2. So maybe you could think faster. Okay, I can put the CO2 inside of the vesicle, inside of the cavity, but then you have to have the connection of this cavity, and it seems that this connection is not that much. However, you have the aquifer in the Serra Geral, you have the water in the Serra Geral, so you have this aquifer, so the percolation can happen, the permeability and porosity can happen there. But it seems that's not exactly about the cavities, it's related with the fractures. But okay, you've been working with the massive basalts, the basalt with vesicles and amygdals, and some of the amygdals filled with some kind of minerals. The zeolite is awful to work with because they're very stable. And once we perform the experiment, zeolite wants to crystallize. And also, you have this interaction in between the sandstones plus the basalts. And this interaction could be nice. So because of this, I was asking you about the Rio Bonito formation because, okay, you see. So I don't have the results for all of these 3 units. I just have the results for this one. That's we're going to go through this presentation here. Yes. So those are the conditions that we've been working with. So I decided to work with this kind of pressure around 70 to 100 bars. We also are working with the 2 kind of, okay, I didn't tell you. You've been working with, you get the CO2 and you're working in this kind of a reactor, hydrothermal reactor, where we put water, the sample, the rock itself, and we pressurize with the CO2. So we promote the reaction of the CO2 plus water. So CO2, it's a very complex reaction, but it becomes bicarbonate, carbonate, and carbonic acid, and it drops a lot the pH, so the system became very, very reactive. However, you have this head space of the reactor filled with a mixture of critic CO2 plus vapor of the water. So you have this kind of, something is happening in the head of the reactor, and something else is happening in the solution, and we think that we are seeing what's happening in the rocks immersed in the solution of water plus the CO2 that's dissolved inside of this water. Also, we've been simulating two kinds of conditions. We've been working with seawater conditions. We put the water that mimifies the seawater, and we also want to work with these freshwater conditions. And depending on the results, then the idea of the project is having this huge amount of composition in between the fresh and the seawater composition, because when you use these parameters, you are working with the ionic force strain, ionic strain. Ionic strain makes lots of dramatic change in the activity of the elements. So we expected that in high ionic strain, what means seawater conditions, we precipitate carbonates faster than in freshwater condition that has low ionic strain. So the activity of the elements is very high, and it's very difficult to reach the saturated index anyway. So we're going to see, so this is our reactor. Here's the scheme that I was talking to you. So we pressurize this with CO2. Probably here in this condition we have the critic plus a little bit of vapor of water. But here we have the CO2 that was dissolved that's reacting with the rock itself. So we're going to see the results now. Okay, that's the composition of the basalts that I've been working with. That is spread here. You can see that's very close in terms of composition of the basalts that's in Iceland and the ones that's Colombia. So it's very, in terms of chemical composition, it's very close to Valula and carb-fix basalt, but have a difference in terms of mineralogy. Here are the mineralogy that you have here. So basically, plagioclase, pyroxenes, CPX, ilmenite, magnetite, chlorite, and some clay minerals as well. Okay, some have some texture and blah, blah, blah. I will pass through. And here are some of our results. We've been working 5, 10, and 20 days in these experiments, and what we've been observing that was very fast for us, very interesting, is that this precipitation of silica, because of this I asked you, it seems that the dissolution happens very fast. In precipitation of silica, it happens fast as well. So here you see the grains itself and this sort of plates of silica that start crystallizing in the reactor. Generally, it's spreading the grains as well, but it prefers the wall of the reactor. I don't know why. It crystallizes or it precipitates. I don't know if it's crystalline silica. I think that's amorphous silica. But it prefers the reactor wall, and it grabs there, and it's very difficult to take this off. When you go further to 10 days, for example, you see lots of dissolution in the minerals. All of these are the features of dissolution in different kind of minerals, in plagioclase and augite as well. Please. So the picture before, it was in pyroxene, and here is the pyroxene with this kind of feature of dissolution. The plagioclase has also features of dissolution as well. That's very interesting. Please. More dissolution, but finally some kind of a precipitation. We started with some chloride precipitations here. That's this kind of funny, tiny crystals that happens here. Please. And what happens, because we are working with the seawater composition, you see crystallization of sulfate, calcium sulfate, that's beautiful like this. It crystallizes a lot. And please, finally, in 20 days as well, we finally saw some crystallization of magnesite. What are you seeing when we work with batch experiments? It seems, okay, you are not talking about the flux the dynamic flux, and etc. It seems like, okay, you have the reservoir, you put everything there, you spend lots of time and see what happens. When we work with this batch kind of experiments, we want to see the equilibration, the equilibrium of the thing. And so you need to go further because you stopped in 20 days experiment, so you need to go to 60 days. So it's a little bit too much because 60 days means that you have 20 days before, so it's 80 days. So it's still running the 60 days. So we are going to see if these magnesites are stable. We hope that the calcium sulfate disappeared because if you want to think about the injection, for example, probably the sulfate is going to clock the injection, the pipes, because it crystallized before the magnesite. So you have to concern about this anyway. We're going to see this in probably the next workshop. We're going to have this kind of results. And here, I want to show you, here's the days that we've been running the experiments. And here is the analysis that happens in the iron. You see, we've been trying to specialize the iron 2 and 3. And what you are seeing here, you have the decreasing of the iron 2 and increasing of iron 3. So during the reaction of the capture of the CO2, you also are promoting some kind of redox reactions. And please, okay, we are trying to monitorize the cations of the solutions, what's happening with the cations of solutions, so we can see the dissolution, for example, it starts here. All of this, especially in these two cations, calcium and magnesium, so you see that's increased the amount in the solution, then decrease, and then it starts funny. So probably here you can see the crystallization of something that's grabbing the magnesium, is the magnesite, and the calcium, for example, it was grabbed by the calcium sulfite, and then probably it's going to be released after. You're going to see what's happening in more experiments duration. And here you see what happened with the pH. The pH drops from the initial to 20 days, but the alkalinity climbed up. What we expected is the alkalines get higher in order to crystallize the carbonates. But we are afraid about the dropping of the pH, because the dropping of the pH is going to dissolve again the carbonates. In the best way, in the best situation, you would crystallize magnesite instead of calcite, because magnesite resists better compared to calcite. And here it was a surprise for us. Remember that I showed you that you have this kind of redox reaction that was happening because we saw the change of the iron 2 to iron 3. So we decided to measure the gas as well, and you see that from 5 days, here is the concentration. Let's see this graph here. Here in this side, you have the hydrogen concentration, and here you have the methane concentration. So from 5 days, you didn't see anything. In 10 days, you can see the production of both hydrogen and methane. And from 10 days to 20 days, you see this huge increase of hydrogen and methane. So you keep thinking that, okay, it seems that you can store carbon via carbonates, but we also can promote hydrogen generation. We're trying to promote generate hydrogen. However, as you can see here, you have it seems that there is a competition. You can produce hydrogen, but we also produce methane. Okay, hydrogen, that's beautiful. Methane, it's awful. So how to deal with this and how to make changes in the system in order to favorize the production of hydrogen and take the methane out of the system. So that's what we've been trying to work with, because either we are in this kind of Sabatier reaction, or we are in the Fischer-Tropsch kind of reactions. We need to understand which one is the one that we've been working with. Probably we are in this kind of reactions because you have this kind of system that happens in this kind of range of temperature, this kind of pressure. So probably you are here and are trying to avoid the methane. So currently, we are trying to store the CO2, but we are trying to understand the competition in between the carbon and hydrogen generation in order to make the reactions go this way and not this way, to mineralize carbon and also produce hydrogen. Okay, that's finished, that's end. Thank you for, I will leave you with this picture of Porto Alegre, and thank you for all of the institutions and laboratory and for you as well. Questions, comments?
Yeah, questions.
Suggestions? Bill.
Thank you, Romy.
Thank
in
you.
the first part of your talk, in the high temperature system, sorry, you suggested that water and CO2 was coming out of the mantle. And I think what you were suggesting was that you were making abiotic carbonate. And if you are making abiotic carbonate, very entertaining idea, do you have geological evidence for that?
Well, we have some evidence. It's spread everywhere. We have some evidence. I don't remember the name of the place that you put fire in the gas that's climbing up. No worries about. So in the beginning, we were thinking about this abiotic generation of hydrocarbons. But it's so hard to publish papers on this, saying that you have this kind of origin of abiotic carbon. Okay, we have in Brazil have this pre-salt reservoir, and the carbon that is the carbon that's in the carbonates, the composition, the isotopic composition, the helium composition, the trace elements composition, suggests that this carbon came from the mantle. So lots of people think about this. So this carbon came, a huge amount of carbon came from the mantle. Because of this, I was thinking, okay, if this carbon came from the mantle by degassing, what if the mantle was changed in terms of oxygen for gas? A plume, a very reducing plume that comes up and decrease the oxygen for gas in the mantle. So what could happen with this kind of, with the CO2 that's coming up? Okay, we've end up in this abiotic hydrocarbons. I don't believe that the hydrocarbon from pre-salt is abiotic, but I think that probably it has some increments of this because the quality of the oil is very interesting. It's very different from the oil from the post-salt, for example. Okay, it could be a catalyzer. It could change the rendement of the, how to say, the rendement of the reaction of the hydrocarbon reaction efficient. Thank you. I don't know. That's something that we want to work with. So we are having another poster with maybe, I know, we started working with this because we are, but not for this workshop. We are very interested in diamondoids to see if you can stabilize diamondoids in this kind of condition. So it's the work of Davi Kanazawa that's here, but in this workshop, we're going to show you something else. So it's still a tricky question. We are still thinking about stabilize not just hydrocarbon, but different kind of species. And currently, you are focused on this kind of things, but also with diamondoids. We think that diamondoids could give us some clue about this kind of things. Yes. I was in Russia last year, and I showed this kind of result, and they told me, okay, that's obvious for us. But you know, yeah.
Okay, more questions?
Questions?
Congratulations for the presentation. In case of the Serra Geral basalt, there will be a best favorable depth in order to CO2 capture?
Yes, that's, then you bring back. That's, for me, no and yes. No, you don't have the, what the depth could help us is the thermal gradient. But the thermal gradient is so low, it goes 45 degrees or 60 degrees in depth. The temperature, for example, we've been working 160 degrees, so it's far from the natural conditions. But what you can see, that's the kinetic of this reaction happens faster. So if the depth, our thermal gradient could be higher, so the depth could be a contributor, because it could start in deeper level of this basalt because of the temperature. But in the real situation, I don't think on this. However, we need to understand, for example, in our case, we want to store CO2 and we want to produce hydrogen. We need a seal. What could be a seal? You need something to trap all of this. Even the way that we are monitoring our experiments is the batch. So it means, okay, you put everything there, you wait ages or not, you are going to see, because we are trying to understand the kinetic of the reactions. But you need the seal. So probably the depth, to answer your question, maybe I could think about, okay, maybe the weight of the stone itself is going to make the seal. When you start this kind of project, I was thinking about having the silica that was happening here, because they dissolve and they precipitate fastly, to make this crystallize in order to, this kind of crystallization, make the seal that you have in order to trap the hydrogen or something that's going to be produced down below. So I'm not sure if the depth, but the composition, the mineralogy composition. I couldn't go through too much because of the time, but the clay minerals, they play lots of roles on this. So it's very interesting, this kind of minerals. We've been make some kind of thermodynamic modeling. Thermodynamic modeling say, okay, go to all guides, per sense. But in fact, the experiments say go to clay minerals because they produce lots of cation. So depend on the depth that mineralogy. I would go to mineralogy instead of depth.
Hi, Rommulo, nice talk. About the Serra Geral formation, you show results about the chemical reactivity, which means the mineralogy component of this problem, but it's also important the physical properties, which means the permeability, the porosity of the formation. Can you say something about the Serra Geral formation, the porosity, because it's important to the kinetic reactions, and you need to have your plume migrate through the formation, and this is something that is that Rio Bonito formation is good because of the permeability and porosity. It's not so good in the chemical reactivity comparing to the Serra Geral, but it's better in the physical properties. So you need to have a balance. But can you mention something about it?
There is a group, I'm not going to this because that's another university that focuses on the permeaporosity of the rock. You're focused on the chemical reactions and mineral reactions and things. But as I was saying, okay, you have the aquifer in the Serra Geral, so maybe you have porosity and permeability. In the beginning, I was thinking about the bubbles, the cavities of the Serra Geral in the vesicle layers of the volcanic. But when you see in microscope image, you see that there is not enough connection in between them. So they have porosity, but they don't have permeability. So that's the frustrating thing. However, in our experiments, I couldn't go through this. As I was explaining, the clay minerals, they are very reactive, and they are interconnected. And because of this, I think that we are very nice working Rio Bonito samples, because I think that we are going to be in a very tricky thing, because I think that we are going to produce lots of silica that's going to be annoying for you because it needs to precipitate somewhere, and the precipitation of silica is very fast. However, on the top of the porosity, the natural porosity that has the Rommulo formation, because it's sandstone and blah, 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 and has permeability and porosity, we will also have clay minerals, and they are very reactive, and they produce lots of cations that's going to be used for carbonatation. So, yes. So in Serra Geral, probably you are going to have some problems in terms of permeability because we depend on the fractures, and we've been working you are making some statistics of the fractures, trying to see how they are connected. So I would guess in this fracture system, not in the cavity itself. But on the top of this fracture system, we also have this interconnectivity of the clays. So once they start reacting with this solution that we have to make the best composition, then they will promote permeability on the rock. That's I will bet on this.
Thank you.
Okay.
So we finished today, and this was our last talk. So tomorrow at 9 we come back. Okay.
Essa questão